Hi everyone and welcome to this short video about sequences. In this video we will learn what sequences are, including their formal definition and notation, talk about some of their important properties, and finally also about bounds, limits, and convergence of sequences. Let's start with the definition. A sequence can be understood as an ordered list of elements. So again, like in sets or in sums, we deal with elements. Mathematically, a sequence can be expressed as a mapping where we have the natural numbers as the main and some set M as the codomain, and N maps to the image Xn. So basically, it is just a special type of mapping or function that only takes natural numbers as inputs. The notation of a sequence is usually Xn with a small n element of the natural numbers, or even shorter, simply Xn. To better understand the concept of a sequence, you can see two examples here. The first one, AN, is a list that starts with a 1, then a 2, 3, 4, 5, and so on. So basically the ordered list of all integers. The second one, BN, is the ordered list 0, 1, 1, 2, 3, 5, 8, and so on. This is actually a very special sequence called the Fibonacci sequence. Maybe you can already see the pattern in it. If not, don't worry, we will get back to it later in this video. Now let's talk about some important properties of sequences. As already mentioned on the last slide, the order of the elements of a sequence matters. Additionally, values can appear several times, so a sequence can, for example, contain the element 1 not only once, but infinitely often. These 2 points, that the order matters and that the value can appear more than once, are the main 2 differences to sets. If you think back to sets, there each element value was unique, so no doubles were allowed. And also the order of the elements did not matter. But back to sequences now. Sequences can be either finite or infinite, and their length is the number of the elements they contain. As the order of the elements matter, they are enumerated and denoted via their index. The example on the slide should make this clearer. We have the sequence Bn that is the 0, 1, 1, 2, 3, 5, 8, and so on. And we start the indexing with A1. So B1 is our first element. In this case, B1, the first element, is a 0. The second element, B2, is a 1. The third element, B3, is also a 1. The fourth element is a 2, and the fifth a 3, and so on, so B6 would be 5, and B7 would be an 8. This is very intuitive, and you only have to look at the element at that exact position. So now that you have a general idea of what a sequence might be, let us look at a sketch. Here you can see the sequence Xn. On the x-axis we have n, which is the index, and on the y-axis we have xn, so the corresponding element of our sequence at that index. You can see that sequences behave like functions. We just don't have a function line, but simply a mapping that only considers the positive integers. In the example here we have the sequence xn equals 1 divided by n. Therefore, the first element of the sequence, which would be denoted as x1, would be 1 divided by 1, so 1. The second element of the sequence, x2, would be 1 divided by 2, x3 would be 1 divided by 3, x4, 1 divided by 4, and so on. So visually, we can understand sequences as ordered collections of these dots, representing the element values. Let's continue with different notations for sequences now. There are 2 different ways of how sequences can be notated, which are explicit notations and recursive notations. An explicit notation means that the value of the nth element of a sequence can be directly read from the definition of the sequence. This means that in the notation itself we have explicitly stated how to calculate each element and simply need to plug in the index value. The first example here is an equals n. You can see that for any element of the sequence we can directly obtain its value from the definition. In this case, this is very easy. The definition says that if we want the nth element, we simply have to use n as a value. So the first element would be a1 equals 1. And this works for any following index as well. A100 would, for example, then simply be 100. All you have to do is using the index value as n. For the sequence Cn, this is the same. It is defined as Cn equals 1 divided by n. Again, we can simply use the indexing here. You can easily read the value of any element of the sequence from the notation. If you, let's say, want to know the value for the element C100, you plug in 100 for n, leading to 1 divided by 100. This is also the sequence you saw on the previous slide. While the explicit notation for sequences is quite easy to handle and work with, there's also the recursive notation, which works a bit different. Here we do not base the value for an element at the index n only on this n, but take other previous elements into account. This might make the calculation of the elements, especially for later elements, more complicated, but it can also be very useful. One important thing to mention is that you always need a starting value, so the first element of the sequence, and depending on the sequence's definition, you might even need more of the elements given in the beginning. Now let's look at examples here. The first one is defined as an equals an minus 1 plus 1, and has already given the starting value a1 equals 1. So we know that the first element is 1. For the second one, we use a formula, which would then yield a2 equals a1 plus 1. So we would have 1 plus 1, which is 2. For the next element, we would do the same, so a3 would be a2 plus 1. This can be done for any further element. The second example is a sequence that we have already seen before, namely the Fibonacci sequence. It is defined as Bn equals Bn minus 1 plus Bn minus 2. So you always add the last two elements to get the current one. The starting values need to be given because in the formula you always need to use the previous two elements. We will calculate the first elements together on the next slide. So by now you should be familiar with the two different notations. To sum it up again, the explicit notation is really only based on the index n, while the recursive notation is based on the previous sequence elements. To deepen the understanding of how to read and understand sequences, you can find several examples here. Let us quickly take a look at the definition of each sequence and then use it to calculate the first elements of the respective sequence together. The first one here is an equals 1 divided by n. It is an explicit notation. All elements can be calculated directly from their index n. Therefore, for the first element, the only thing we have to do is to take the 1 as the index. So we simply plug in a 1 for n. For the second one, we plug in a 2, and for the third one, a 3, and so on. This results in the first elements 1 divided by 1, which is 1, then 1 divided by 2, then 1 divided by 3, 1 divided by 4, and so on. For the Fibonacci sequence, here given in the example Bn, the first element is 0 and the second element is 1. The third element, B3, would then by definition be B2 plus B1. So in this case, 1 plus 0, which is 1. B4 is then B3 plus B2, so 1 plus 1, which is 2. This goes on like this, so the next element would be 2 plus 1, which is 3. Then we would have 3 plus 2, which is 5. And then 5 plus 3, which is 8. And this continues like this. The third example is again a sequence that is given by recursive notation. It is defined as 5 plus Cn minus 1 divided by 2 times Cn minus 1. And it has the starting value C1 equals 1. Now we can start calculating the next elements. For C2, the formula yields 5 plus C1 divided by 2 times C1, which is in our case 5 plus 1 divided by 2 times 1, so 6 divided by 2, which is 3. For the next element, we would have to use the 3 that we just calculated, so it would be 5 plus 3 divided by 2 times 3, which is 8 divided by 6, and it can be reduced to 4 divided by 3. For the next element, we need to use the 4 divided by 3. So we would have 5 plus 4 divided by 3 divided by 2 times 4 divided by 3, which should result in 19 divided by 8. After these few examples, you should now be familiar with reading and understanding sequences and their notation. Let's continue with the next topic. Now I want to introduce the concept of bounds. If a sequence an is bounded from above, it means that an is smaller or equal to some value x. So an stands for the whole sequence, meaning that every element of the sequence has to be smaller than x. You can think of it like an actual bound. All elements of the sequence are below or equal to this bound. Now, if a sequence is bounded from below, this is the same concept, but the other way around. So all elements from our sequence are greater or equal than a specific value x. If a sequence is bounded from above and from below, we call it simply bounded. So all elements of the sequence lay in between two values, namely the bounds. Let us take a look at this in a visualization. Here you can see 4 examples of sequences. As before, the sequences and their elements are represented by yellow dots. The red lines refer to the bounds now. In the first example, we have a bounded sequence. All elements are below or equal to the upper bound, and additionally, all elements are greater or equal than the lower bound. So they all fit in this range between the lower and the upper bound. The example on the top right, however, is only bounded from one side, namely from below. We can clearly see that each element is bigger or equal to the lower bound, but we cannot draw any upper bound. So no line would fulfill the requirements of bounding all elements from the sequence from above, as the sequence is growing infinitely large. This is drawn with a gray asymptote. You can see that it will be growing infinitely large, as seen before, so the gray line goes very large and steep, and nothing can bound it from above. The example on the bottom left is again a sequence that is bounded. The red lines here indicate upper and lower bound again, and all values from the sequence fit inside this range. And in the last example, I want to show you a sequence that is not bounded at all, so not from above and also not from below. You can see that its values are growing in both directions, which makes it impossible to put all values over or below any bound. In gray, you can see again the asymptotes, which make it clear or show that it is growing infinitely large in both directions and cannot be bounded. The next concept we want to talk about is limits. Generally, we are often interested in the limit of a sequence, which means we want to know what happens for an infinitely large n, so the very late elements of our sequence. You write this like limes n against infinity of an, meaning you are sending n towards infinity to take a look at what happens in such a case. Now, only if this results in a concrete value, we call this value the limit of the sequence. Limits are closely connected to convergence of sequences. There are 2 main concepts here, namely convergence and divergence. We call a sequence convergent if it converges towards a concrete limit. If this is not the case, so if we cannot find a real limit, we call the sequence divergent. There are 2 different types of divergence. The first one is definite divergence. This is the case if the sequence goes to infinity or minus infinity for very large n's. An example is the sequence an equals n. It grows infinitely large, so it does not have any real value as a limit, but diverges towards infinity. The other type of divergence is indefinite divergence. Here it does not diverge into a specific direction, so to infinity or to minus infinity, but it somehow alternates and we cannot find any concrete limit of the sequence. The first example is the sequence bn equals minus n to the power of n. Here the sequence's elements are -1, 1, -1, 1, -1, and so on. There are no concrete limits here, and the value or values towards which the sequence converges, it will always switch between -1 and 1. The second example is -1 to the power of n times n. We also have this alternating component of positive and negative here, but now we also multiply it by n. This means the sequence will always switch between a large positive and a large negative value for very high n's, so it will grow in both directions to infinity and -infinity respectively. No limit can be found here. It is important to mention that for indefinite divergence, the sequence does not necessarily have to go to infinity or -infinity for large n's, but a sequence that alternates like Bn here is also divergent. Now let us take a look at the graphic that shows some examples. Here you can see 4 different sequences, which are the ones you've already seen before. In the first case, we can see that the sequence approximates a concrete value after some time, so it converges to this value for an infinitely large n. The example on the top right is divergent because the sequence elements will grow infinitely large. As it only grows towards infinity, we call it definite divergent. The example on the bottom left is convergent again. After some time, the value will not change a lot anymore, and for an infinitely large n, all the values will approximate a concrete value. The last example shows indefinite divergence. The sequence does not have any limit and also no definite direction into which it grows. It grows both to infinity and to -infinity. Now let's take a look at the formal definition of convergence. Convergence also has a formal definition, which might look a bit complex, but it is actually not. So let's read it together. We say that a sequence xn converges to a limit, which we call x, if the following holds. For every epsilon that is bigger than 0, there exists an n0, which is element of the natural numbers, so that for every n that is bigger or equal to this n0, it holds that the difference between the sequence at all the indices from n0 on, so all the xn's after or from the starting point, and the limit x are smaller or equal to epsilon. So in other words, this means that for any epsilon that we choose that is bigger than 0 but can be very, very small, there is an element in our sequence, n0, from which on the differences from the element values to the limit of the sequence are so small that they will all stay in the range of the epsilon around our limit. So this means that the element values do not change a lot anymore, only so slightly that the changes are as small as epsilon. And this works for any very small epsilon, even if you choose a super small one. How to find out whether a sequence is convergent or not and how to calculate its limit will be covered in a third video this week. A special type of sequences that will be more important later on are zero sequences. A zero sequence, or also called null sequence, is defined as a sequence that converges to 0, as the name already indicates. The figure here shows 3 examples. The first one is a sequence that approximates the 0 after some time from above. The second one comes from below, and the last one is alternating, but it also approximates the 0 after some time. An is here a sequence that you have already seen several times before in this video. It is 1 divided by n. When you think about its limit, you have to send n to infinity. So what happens when you divide 1 by something infinitely large is that it approximates to 0. Therefore, an is a zero sequence. This is already it for the introduction video to sequences now. So by now you should be familiar with the general concept of a sequence, the 2 notation types, and the concepts bounds, limits, convergence, and divergence. I hope you liked this video and see you again next time.